Welcome to our deep dive into the mechanics of semantic search. To understand how modern AI finds what you need, we first need to look at the fundamental interaction of search. It all starts with you, the user. You have a problem, or an intent, which you express in natural language. For example, you might type how to fix a leaking tap. Notice the phrasing. It's human, conversational, and specific. On the other side of the equation, we have the destination. This is the knowledge base. A massive, structured collection of documents, articles, and data points waiting to be retrieved. The challenge of search is simple to state, but hard to solve. How do we connect your messy, human intent with the precise information stored in that database? Historically, this has been a battle between two very different approaches. Is the machine just matching the words you typed, or is it actually understanding the meaning behind them? To appreciate the power of semantic search, we first need to understand the limitation of the traditional approach. Lexical search, or keyword matching. Let's say a user searches for automobile repair, and in our database, we have a relevant document titled Car Fix. Now, as humans, we instantly know these two phrases refer to the exact same service, but a traditional keyword engine is literal. It looks for the string automobile inside the document, and it finds nothing. It then looks for repair, and again, no match found. Because there is zero lexical overlap, no shared keywords, the search engine returns a 0% match. This is the vocabulary mismatch problem. The syntax is different, but the semantics, the meaning, is identical. To solve this, we need a way for computers to stop matching letters and start matching meaning. That is where vector embeddings come in. Let's look at a classic challenge in search. The problem of polysemy. Polysemy is simply when one word has multiple meanings. Take the word bank. To a computer reading text characters, this is just BANK, but conceptually it branches into two completely different worlds. On the left, we have nature, the land along a river. On the right, a financial institution. Now, imagine a user searches for bank money deposit. We know they are looking for a place to store cash. However, a traditional keyword search might latch onto the word bank. It matches the string perfectly and could erroneously lead us to documents about river banks, perhaps ignoring the context entirely. Obviously, this is a failure. The keywords matched, but the meaning didn't. Semantic search works differently. It ignores the ambiguous keyword overlap and focuses on the context. Money. It understands that money is semantically related to a financial institution. By matching these meanings, or vectors, it correctly routes the query to the financial bank, even if the exact keywords in the document were different. This ability to disambiguate based on context is the superpower of vector search. To understand how semantic search works, we first need to bridge the gap between human communication and machine logic. Take, for example, the word king. To you and me, this represents a concept, a monarch, a ruler, a piece in chess. But to a computer standing alone, this is just a string of characters. It has no inherent meaning. To solve this, we pass the text through an embedding model. Think of this model as a sophisticated translator. It converts that text into a long list of numbers, known as a vector. So, while we see the word king, the computer sees a specific coordinate in a multidimensional space. 0, 2, -0, 5, 0, 8, and so on. This transformation is the foundation of everything that follows. Because while computers cannot calculate the distance between words, they can easily calculate the distance between numbers. To appreciate the power of semantic search, we first have to look at the traditional way computers handled text, often called one-hot encoding. Imagine we have a very small vocabulary consisting of just 3 words: cat, dog, and fish. In this system, we convert each word into a list of numbers, or a vector. We assign each word a unique slot. Cat gets a 1 in the first position, and zeros everywhere else. Dog gets a 1 in the second position, and fish gets a 1 in the third. This looks simple, but it creates two massive problems. First, look at all that empty space. If our dictionary had 10,000 words, each vector would have 1 and 9,999 zeros. We call this sparsity, and it's incredibly inefficient. Second, and more importantly, notice that cat and dog occupy completely different slots. Mathematically, they don't overlap at all. Even though we know cats and dogs are both pets, to the computer, these vectors are completely unrelated. They are orthogonal. There is no shared meaning here, just rigid indexing. To solve this, we need a way to capture relationships, not just positions. Building on the bag of words approach we just saw, we were left with this, a sparse vector. Notice how it is tall, rigid, and filled mostly with zeros. It effectively tells us which words are absent rather than what the text means. To solve this, semantic search utilizes what we call an embedding. Technically, this is known as a dense vector. Unlike its sparse counterpart, look at how compact this is, but the real magic lies in these numbers. In an embedding, every single value represents a specific, abstract feature of the text's meaning. One dimension might capture gender, another plurality, and another verb tense, though in reality, these features are often far more abstract. While the sparse vector just matches keywords, the embedding places the query into a meaningful, multidimensional space. Now, let's see how we actually use these dense vectors to find similarity. To understand how the computer understands meaning, we need to visualize where these embeddings actually live. Let's imagine a multidimensional vector space, represented here by a simple 2D graph. When the system processes a word like apple, it converts it into a list of numbers. These numbers are coordinates. In this vector space, apple becomes a specific point, a vector pointing in a specific direction. Now, what happens when we process a semantically similar word, like banana? Because banana shares context with apple. They are both fruits, they are both food. The embedding model assigns it numbers that are very similar. See how they land in the same neighborhood. Their vectors point in almost the same direction. In contrast, let's look at a completely different concept. Car. A car has no semantic relationship with fruit. Therefore, its mathematical coordinates place it far away, pointing in a completely different direction. This acts as a map for the computer. To find relevant results, the search engine simply measures the distance between these points. Short distance means high similarity, while a long distance signals that the topics are unrelated. This geometric proximity is the secret to semantic search. To understand how the computer actually sees this relationship, let's zoom in on that fruit cluster and look at the vector space directly. Here we have the vector for apple. Its position is determined by the numerical values in its embedding, and right next to it, we plot the vector for orange. Because these two words share many contexts, they are both fruits, round, and edible. Their embeddings are mathematically very similar. In this geometric space, similarity is simply the straight-line distance between the tips of these arrows. We call this semantic proximity. Notice how short this line is. To the search engine, a short distance means a high probability that these words match the same intent. Now, what happens if we introduce a word with a completely different meaning? Let's plot the vector for car. Mathematically, car has almost nothing in common with apple. It appears in totally different sentences. Consequently, its vector points in a different direction, landing far away in the graph. If we measure the distance between apple and car, we see a massive gap. This is the core mechanic of semantic search, calculating these distances. A small distance implies a match in meaning, while a large distance implies the concepts are unrelated, regardless of whether they share any specific letters or keywords. So far, we've visualized these vectors as arrows on a simple 2D plane, or perhaps in three-dimensional space, adding depth to our coordinates. But human language is far too nuanced to be captured by just 2 or 3 coordinates. We need more room. In the world of semantic search, models like BERT don't stop at 3 dimensions. They operate in high-dimensional space. Imagine this vector extending not just along an x, y, and z axis, but along hundreds of independent axes simultaneously. For a standard BERT model, every single piece of text is converted into a vector with exactly 768 dimensions. That means the meaning of your query is encoded as a specific sequence of 768 numbers. Even though we can't draw an arrow in 768-dimensional space, the math remains the same. We are simply looking for the closest match in this massive list of numbers. To understand how we get these numbers, we need to look under the hood at the engine powering semantic search, the neural network. Specifically, a model trained to convert language into lists of numbers. Let's say we want to process the word king. When we feed this text into the network, the information doesn't just sit there. It flows through layers of artificial neurons. These hidden layers process the relationships between words, calculating complex associations, until finally, the network produces a specific output. This output is our vector embedding, a unique coordinate representing the meaning of king in a multidimensional space. But here is the key. The network isn't guessing. During a massive training process, it adjusted the strength of all these connections, learning exactly how to map words with similar meanings to similar vectors. Once trained, this black box becomes our embedding generator. Now, to truly understand semantic search, we must understand how modern models handle nuance. Let's look at the role of context. Consider these two sentences. In the first, we are depositing money. In the second, we are sitting by a river. But look closely at the final word. We see the word bank in both. To a simple keyword search or even older embedding models, these might look like an exact match. But semantically, they are worlds apart. Modern models, like BERT or those using transformers, don't read words in isolation. When the model reads the first sentence, it sees deposit and money. It uses this context to generate a specific vector for bank that aligns with financial concepts. However, in the second sentence, the model sees sit, river, and on. It realizes this bank is a geological feature. Consequently, it generates a completely different vector representation. This is the breakthrough: contextual embeddings. Even though the text input is identical, the vector output is unique to the specific meaning in that moment. This ensures that when you search for financial institutions, you don't get results about river sides, even if the word bank is used. To understand how the engine captures this meaning, we need to look inside the architecture used by modern semantic search, the transformer encoder. Let's take 3 tokens from a query: global, warming, and impact. On their own, warming could mean getting cozy under a blanket, and impact could be a font type, but the model uses a mechanism called self-attention. Notice how the model looks at global and impact to update its understanding of warming. It creates a web of relationships, realizing that this specific warming is about climate change. This creates a context-aware state within the transformer block. The model is no longer looking at isolated words. Finally, this contextual understanding is projected into a dense vector, a list of numbers representing the specific meaning of these words in this specific sentence. These are your contextualized embeddings. Unlike simple keyword matching, these vectors now carry the deep semantic relationship of the entire phrase, ready to be compared against your database. Moving on from individual words, how do we capture the meaning of an entire thought? First, the model looks up the embedding for every single token in the sequence. We now have a list of vectors, 5 words, 5 distinct mathematical directions, but a semantic search engine can't store a variable list of vectors for every document. It needs a single, fixed-size fingerprint. To get this, we perform an operation called pooling. Specifically, mean pooling. Don't let the name intimidate you. It is simply taking the average. We add up all the word vectors dimension by dimension, and divide by the number of words. The result is a single sentence embedding. This one vector captures the essence of the whole sentence, blending the fox, the speed, and the action into one coordinate. To understand how we actually teach a machine to recognize meaning, we need to look at the training architecture. This is often called a Siamese network, or sentence BERT. It's called Siamese because it consists of 2 identical BERT networks side by side. Crucially, these aren't 2 separate brains. They share the exact same weights. Think of it as passing 2 different pieces of paper through the same photocopier. Any update to one side immediately updates the other. During training, we feed the model pairs of sentences. Here, we have the cat sits and a feline rests. To us, these clearly mean the same thing. The network processes each sentence independently. It applies its attention mechanisms and feed-forward layers to distill the information. The output of this process is a fixed-size embedding vector for each sentence. Let's call them vector U and vector V. Even though the input words were different, cat versus feline, we want their numerical representations to be very similar. Finally, we compare these 2 vectors using a similarity metric, typically cosine similarity. The goal of training is simple. Maximize the similarity score for synonymous sentences. By adjusting the network's weights to pull these vectors closer together, the model learns that cat and feline share a semantic neighborhood in this high-dimensional vector space. Once we have our text converted into embeddings, how do we actually determine which ones are related? We need a way to measure the closeness between these vectors in our semantic space. The most intuitive metric is Euclidean distance. Geometrically, this is simply the straight line connecting the tips of two vectors. You might recognize this from high school geometry. If we look at the coordinates, the distance d is calculated using the familiar Pythagorean theorem formula shown here. In a semantic search context, a shorter distance usually implies higher similarity. However, there is a significant limitation when applying this to natural language. Semantic meaning is primarily encoded in the direction of the vector, not its length. Imagine we have a short article about space travel, represented by vector b. Now, imagine a much longer book about the exact same topic. The vector points in the same direction, but because the book has more words and higher term frequencies, its magnitude increases. Look what happens to our distance metric. Even though the topic is identical, the Euclidean distance d has grown significantly, suggesting these documents are very different. Because it is sensitive to magnitude, Euclidean distance isn't always the best measure for semantic similarity. We need a metric that cares only about the angle. To a computer, semantic similarity isn't a feeling, it's a calculation. Specifically, it's an operation called the dot product. Let's look at our query vector, A, and a document vector, B. While we visualize them as arrows, the computer sees them as lists of numbers or matrices. To calculate how similar they are, we check their alignment dimension by dimension. First, we multiply the corresponding components of the first dimension. Then, we do exactly the same for the second dimension. If we had more dimensions, like the hundreds used in real AI models, we would keep going, multiplying every matching pair. Finally, to get the result, we sum all these products together. This single number is our total similarity score. Think about what this means. If both the query and the document have high values for the same feature, say, farming, their product will be large, driving the total score up. If they mismatch, the product is low. This is how the math captures the meaning. Now that we have transformed our data into vectors, we face a critical question. How do we determine if a query and a document are actually a match? Let's visualize our semantic space. Here, we have a user's search query represented by the blue vector and a specific document represented by the yellow vector. They are pointing in a somewhat similar direction, meaning they share some semantic context. Notice that the document vector is much longer than the query. Perhaps the document is a long article, while the query is just a few words. In traditional math, the distance between their tips might be huge just because of this length difference. But in semantic search, we don't care about word count or frequency. We care about meaning. To capture meaning, we look at the direction. We measure the angle, theta, between these two vectors. The smaller this angle, the closer their meanings are aligned. In data science, we call this cosine similarity. It is simply the cosine of that angle. A score of 1 means perfect alignment, 0 means no relation at all. The beauty of this metric is that it ignores magnitude. Watch as we change the length of our vectors. Maybe we add more text to the document or the query. Notice that while the arrows change size, the angle, and therefore the similarity score, remains exactly the same. We are matching the essence of the request, not just the volume of keywords. Now that we've visualized these word vectors floating in space, we need a precise way to measure the relationship between them. How do we mathematically determine that king is close to queen but far from apple? We use a metric called cosine similarity. Let's break down exactly how this equation works. The numerator is the dot product of the two vectors A and B. Think of this as the directional alignment. It calculates a raw score based on how much the two vectors point in the same direction. If they overlap perfectly, this number is high. However, there's a catch. The dot product is sensitive to the length of the vectors. In text analysis, a word appearing 100 times shouldn't necessarily be more similar than a word appearing once. We care about the meaning, not the frequency. To fix this, we look at the denominator. Here, we multiply the magnitudes, or lengths, of the two vectors. By dividing the dot product by these lengths, we perform length normalization. This essentially shrinks all vectors to a unit length of 1. By removing the influence of magnitude, the only thing left is the angle between them. The result is the cosine of that angle, a pure measure of semantic similarity ranging from -1 to 1. But raw embedding vectors often come in different sizes. In some models, the length, or magnitude, of the vector might represent the frequency of a word or the confidence of a prediction. However, for semantic search, we are primarily interested in the direction of the vector, which represents its semantic meaning rather than its length. To make comparisons fair and calculations efficient, we perform a step called normalization. We define a unit circle with a radius of 1. Normalization is the process of taking every vector in our database and scaling it, shrinking the long ones and extending the short ones until they all touch this unit circle perfectly. Notice that while their lengths change, their direction stays exactly the same. Why do we do this? It's a massive computational shortcut. Recall our dot product formula. It involves multiplying the magnitudes of the two vectors by the cosine of the angle between them. But since we just forced all our vectors to have a length of exactly 1, these terms become ones. They effectively disappear from the equation. So, for normalized vectors, the dot product is the cosine similarity. This means to find the best match, the computer just needs to calculate a simple dot product, which is incredibly fast at scale. Before we can perform a search, we need to prepare our knowledge base. This is a process called indexing. Think of this as the system reading the library before opening the doors to the public. We take our raw documents, articles, PDF, or web pages, and feed them into our encoder. Inside this neural network, the semantic meaning of the text is distilled and transformed into a numerical vector. This vector is then sent to a specialized storage system known as a vector database. We repeat this for every single document we have. We are essentially pre-computing the meaning of our entire dataset. By the end of this process, we don't just have a folder of files, we have a geometric map of information. Each dot represents a document's specific location in semantic space. This pre-calculation is crucial. It allows us to search through millions of documents in milliseconds later on. With our document index built, we move to step 2, handling the live user query. Let's say a user asks, "What are black holes?" Note that this is natural language, unstructured and messy. To understand this, the system doesn't just look for keywords. It passes this query through a neural encoder. Crucially, this is the exact same encoder, with the same weights and parameters, that we used to index our documents earlier. Why is this important? Because it ensures that the user's question is interpreted using the same rules as the library's content. The encoder processes the semantic meaning of the question, analyzing the relationship between black holes and the intent of definition. The output is a new, unique list of numbers. The query vector. This vector now exists in the same multidimensional space as our documents. Even though the user didn't type the exact words found in a physics textbook, this numerical representation captures the essence of their curiosity. Now that we have our database of text chunks converted into vectors, we enter the retrieval phase. This entire coordinate system represents our semantic index. Each gray dot is a piece of content from our documents, frozen in space based on its meaning. When a user types a search query, that text is also processed by the embedding model and lands at a specific coordinate in this same space. Let's call this our query vector. The goal of semantic search is simple. Find the content vectors that are geometrically closest to this query vector. Because in this vector space, distance represents semantic similarity. Points that are close together share similar meanings. This is where the k-nearest neighbors, or KNN, algorithm comes in. The k represents how many results we want to retrieve. In this example, let's set k to 3. The system calculates the distance from the query to nearby points and identifies the top 3 candidates with the shortest distance. These are the nearest neighbors, the most relevant results that will be returned to the user. Notice that we didn't match keywords. We simply found the concepts that lived in the same neighborhood as our question. Now that we have our query vector, how do we actually find the best match in our database? Imagine this grid represents our database, containing not just 10, but potentially millions of vector embeddings. The most straightforward approach is what we call exhaustive search, or brute force. We take our query vector and we compare it with the first vector in the database, then the second, then the third. We calculate the cosine similarity for every single document to see which one is the closest. Mathematically, this is precise, but computationally, it's a disaster at scale. If you have 1 million vectors, you must perform 1 million comparisons. Even if each calculation takes a fraction of a millisecond, the time adds up linearly. In computer science terms, we call this linear complexity, denoted as big O of n. As your data grows, your search time grows with it. For a real-time search engine handling millions of users, waiting for this progress bar to finish is simply not an option. We need a way to find the closest vectors without checking every single one. Let's see how we can cheat the geometry. So, how do we solve this scalability crisis? We have to make a fundamental engineering trade-off. Let's compare our two options. On the left, we have exact search, the brute force KNN approach we just saw. On the right, the solution, approximate nearest neighbors, or AN. First, let's look at speed. Exact search forces us to check every single vector. As your data grows, this becomes painfully slow, scaling linearly or big O of n. It's a bottleneck. AN, however, uses clever indexing trees to skip most of the data. It is ultra-fast, often scaling logarithmically. But there is no such thing as a free lunch. Let's talk about accuracy. Exact search is, by definition, perfect. It will always find the absolute closest match. AN is, well, approximate. It might miss the absolute best match in rare cases, giving us something that is 99% correct instead of 100%. Here is the reality of semantic search. For millions of documents, trading that tiny sliver of accuracy for a system that is 1,000 times faster isn't just an option, it is the only scalable solution. This is the power of ANN. To perform this search efficiently at a massive scale, we use an algorithm called HNSW, or Hierarchical Navigable Small Worlds. Think of HNSW like a transit map for your data vectors. At the bottom, we have the local streets, layer 0. This layer contains every single data point and is densely connected. Above that, we build simpler, sparser layers. Layer 1 is like arterial roads, and the top layer is like an expressway. These upper layers contain only a few promoted data points with long-range connections. When a query comes in, let's say, looking for machine learning, we don't start by checking every house on the local streets. We start on the expressway. The algorithm enters at the top layer and greedily hops to the node closest to our query target. It takes big steps across the vector space. Once it can't get any closer on this layer, it drills down to the same node in the layer below. Now, on the arterial roads, the search continues. The connections here are shorter, allowing us to refine our position and get closer to the target. Finally, we drop to layer 0. Since we're already in the right neighborhood, we only need to check a few local connections to find the best match. This hierarchical approach allows us to find the approximate nearest neighbor in milliseconds, skipping millions of irrelevant vectors entirely. To implement semantic search, we rely on two primary architectures. On the left, the bi-encoder, often called the twin tower model, and on the right, the cross-encoder. Most vector databases use the bi-encoder approach. Here, the query and the document are processed completely independently. Notice how we get two separate vectors. Because the document vector doesn't depend on the query, we can pre-compute it and store it for millions of documents. Comparison happens only at the very end, usually via cosine similarity. It's incredibly fast, perfect for retrieval. However, for maximum accuracy, we use a cross-encoder. Here, the query and document are fed into the model simultaneously. Inside the model, every word in the query can attend to every word in the document via self-attention. They mix and interact deep within the neural network. Instead of vectors, it outputs a raw similarity score directly. This captures subtle nuances that vector distances might miss. The trade-off: cross-encoders are too slow to run on a whole database. So, in production, we often use bi-encoders to retrieve the top 100 results, and then use a cross-encoder to re-rank just those few for the final, high-precision answer. So we have a dilemma. Bi-encoders are fast but lack nuance. Cross-encoders are precise but too slow for millions of documents. To solve this, modern search systems use a two-stage pipeline, often called the re-ranking pattern. Imagine your entire database of documents at the top. It's simply too massive to check every single one carefully. Stage 1 is the retrieval phase. Here, we use the bi-encoder. Because it creates vectors in advance, it can instantly scan the entire database and filter out a manageable list of candidates. Say, the top 100 roughly relevant items. Now that we have a small, manageable list, we enter stage 2, re-ranking. Here, we unleash the powerful cross-encoder. It looks at this short list and compares the query against every document, one by one, with full attention to detail. Notice how the order changed. The cross-encoder realized that a document the bi-encoder thought was number 5 is actually the best match. Finally, we simply slice off the very top results to show the user. This funnel architecture gives us the best of both worlds, the speed to search millions and the intelligence to understand the nuance. So far, we have looked at these methods in isolation, but in production systems, we rarely choose just one. Instead, we use hybrid search. Hybrid search is the practice of calculating two scores for every document: a keyword match score, like BM25, and a semantic vector score, like cosine similarity. We then combine these two distinct signals into a single, unified ranking using a linear weighted sum. Here, the magic lies in this variable, alpha. Alpha acts as a tuning knob. If you set alpha to 1, you rely entirely on vector semantics. If you set it to 0, you are back to pure keyword search. By picking a value in between, say 0, 7, you prioritize conceptual meaning while still respecting the precision of specific terminology. This mathematical blend creates a robust system that understands context, but doesn't lose sight of exact matches. To wrap up, let's consolidate everything we've learned into a single, cohesive workflow. The journey begins with your input text, the raw query or document. This raw text flows into the encoder, usually a transformer model like BERT, which acts as the brain of the operation. The encoder transforms the meaning into a mathematical vector, a multidimensional array of numbers representing semantic intent. This vector is then organized within an index, specifically designed for approximate nearest neighbor search to handle massive datasets efficiently. When a query comes in, the search algorithm calculates cosine similarity to find vectors that are close in the latent space. Finally, the system retrieves the most relevant content as the result, effectively matching meaning rather than just keywords. This entire cycle, from text to math and back to relevant information, happens in milliseconds. By mastering this pipeline, you unlock the ability to build applications that truly understand what your users are looking for.